Good morning. I welcome you all to this series of lectures on electronic devices and circuits. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, IARE. So today I am going to deliver the lecture on full wave rectifier. Previously we have discussed about the half wave rectifier and what are the advantages of half wave rectifier. It is a very simple circuit consisting only one diode, and because it uses only one diode and less number of components, naturally the cost is less, and we can easily implement it and we can easily construct it, and obviously it has a low number of components, so it is very cheap. So these are the various advantages of half wave rectifier. But the half wave rectifier has some disadvantages. The disadvantages are the transformer utilization factor is low and they produce a low output voltage. The output voltage is less, and the DC saturation of the transformer core, it results in magnetic current and some hysteresis losses and generation of harmonics. So the power output and the rectification efficiency are also quite low for half wave rectifier, because the power is delivered only during one half of the cycle, and the ripple factor is very high, and so we require elaborate filtering to get a smooth DC output. And the half wave rectifier allows only half cycle per sine wave. The other half cycle is wasted. So this leads to power loss and low rectification efficiency. So to overcome these disadvantages, we go for full wave rectifier. So this is the circuit for the full wave rectifier, and this consists of two diodes, D1 and D2. And a center tapped transformer is used, and the input voltage is applied to the primary winding of the transformer. So this is the full sine wave, and when point A of the transformer is positive with respect to C, the diode D1 conducts. So this is the positive point A, which is positive during the first half of the cycle, and when A is positive with respect to C, the diode D1 it conducts. So, and there is going to be a current flowing in the forward direction. Okay, so the current flows in this direction. Okay, and the current flows in this direction, and finally it goes through this resistor, and this is it reaches the ground point at the center point of the transformer. Okay, so the full wave rectifier, it consists of two power diodes, and they are connected to a single load resistance, with each diode in turn taking the supply current to the load. And during the second half of the cycle, what happens? The diode D2 conducts and the current flows in this direction. Okay, so in both cases, the direction of current through the load resistor is same, so we get a full rectified wave. So the full wave rectifier, so let us see here once again. During the positive half cycle, we get a positive wave here and a positive wave here, and this diode it conducts during this positive half cycle, and this diode it does not conduct during this positive half cycle, because this diode D2 is reverse biased and this diode D1 is forward biased. So the current flows through the resistor in this direction, and we get a output this way. So during the negative half of the input cycle, what happens? This D1 is reverse biased and it acts like a open circuit. And similarly, D2 it conducts, and because it is forward biased, so it acts like a closed switch, and the current flows in this direction. So in both positive and negative half cycles, the direction of current through the load resistor is in the same fashion. So for the negative half cycle also we get output. So when the input is like this, the output is somewhat like this. So the wave, the input sine wave is fully rectified, and we get output for both positive and negative half cycles. For both positive and negative half cycles, the direction of current through the load resistor is same. Now let us find out the various parameters for this full wave rectifier. First is the average DC current. So the average value of DC current okay, it is like this. IL is equal to IM sine omega t. And what is the waveform for this load current? It is like this. This is omega t, this is pi, and this is 2 pi, and maximum peak value is IM. Okay. So what is average value? 0 to pi 1 by pi IM sine omega t. So this is equal to 1 by pi Im, and the integral of sine omega t is minus cos omega t, and we have to find out its values, the limits 0 to pi. So we get here 1 by pi Im by pi and minus cos pi minus cos 0. So what is this? Im by pi so this is 1 plus 1. So the average value is 2 Im by pi. So this is the average value of DC current for the full wave rectifier. And what is the corresponding value for the half wave rectifier? We have already calculated. For half wave rectifier, it is Im by pi. For half wave rectifier. So you can easily infer that the average value of current is double compared to the half wave rectifier. The average value of full wave rectifier is double compared to the value in half wave rectifier. So it is better. The average value is better. Okay. Now let us find out what is the average value of DC voltage. So the average value of DC voltage, what is the voltage we have to apply? The Ohm's law, DC voltage, output DC voltage. So EDC is equal to IDC multiplied by RL. RL is the load resistor. So we get here, what is EDC? We have already calculated, the value is 2 Im by pi and multiplied by RL. And what is the Im value? Im is, the peak value of current, which is nothing but 2 into ESM by RL into RL into 1 by pi. So this gives us 2 ESM by pi. So this is the average value of DC voltage for full wave rectifier. And what is the corresponding value for half wave rectifier? It is ESM by pi. For half wave rectifier. So it is better. The performance is better. Now after this, let us calculate the root mean square value of current. So which is called as the RMS value. So RMS value, which is nothing but the root mean square value. So we have to take the value, then square it, then find the mean of it, then take the root of it. So that is a root mean square value. So the value is like this: IRMS square, it is equal to, we have to take the value 1 by pi and 0 to pi and IL square d omega t. And what is IL? IL is equal to Im sin omega t. So this is equal to 1 by pi 0 to pi. IL is Im sin omega t d omega t. So this is Im square and sin square. So this is equal to Im square by pi. And what is sin square omega t? It is nothing but 1 minus cos 2 omega t divided by 2. So we have to find out the integral of 1 minus cos 2 omega t divided by 2 d omega t. So what is the value? So this is equal to Im square by pi. And what is the integral? It is 1 by 2. It is omega t divided by 2 minus sine 2 omega t divided by 4. And we have to find out the values, the limits 0 to pi. So this will give us the value as Im square by pi, and this is into pi by 2. And sine 2 omega t, once you put the pi, 2 pi, it is 0. So we can neglect it. So you get the value as Im square by 2. So this is the RMS value of current for full wave rectifier. So the actual RMS value you get by taking the root of it. So IRMS is equal to Im divided by root 2. So this is the value for full wave rectifier. What is the corresponding value for half wave rectifier? We know the corresponding value for half wave rectifier is Im by 2. So naturally we can say that the RMS value of current is larger than the value which we get using the half wave rectifier. So full wave rectifier is superior as far as the RMS value is also concerned. The next parameter what we are going to discuss is the RMS value of the load current. So load current RMS value, how do we calculate? We multiply the current by the voltage. So the ELRMS, we take the RMS value of current, IRMS, and we multiply it by the load resistance, RL. And what is the RMS value? We have already calculated. It is Im by root 2 multiplied by RL. So this is the RMS value of voltage for full wave rectifier. And what is the value which we have calculated for half wave rectifier? The value for half wave rectifier is Im by 2 multiplying by RL. So this is for half wave rectifier. So we can say that the full wave rectifier is superior as far as the RMS value of output voltage is also concerned. Next, let us calculate the DC power output for the full wave rectifier. DC power output for full wave rectifier. What is the power? Power is nothing but I square R. So that gives us the value of power. So for DC power, we have to take IDC square multiplied by RL. So the DC power output PDC is equal to IDC square multiplied by the load resistance. So this is the DC power output for the full wave rectifier. And what is the value of the DC current? The DC current we have already calculated. It is 2 Im by pi. So it is 2 Im by pi whole square multiplied by RL. So this is equal to 4 Im square by pi multiplied by RL. So this is the DC power output for the full wave rectifier. Now let us calculate what is the AC power input for the full wave rectifier. AC power input for full wave rectifier. So the AC power input we get by multiplying the RMS value with the load resistance. Or what are the load resistances that are involved in circuit? The diode forward resistance, the secondary transformer coil resistance, and the load resistance. So all these three resistances have to be taken into account to calculate the AC power input. So PAC is equal to IRMS square multiplied by the RS plus RF plus RL. What is IRMS square? It is Im by 2. Im by root 2 multiplied by RS plus RF plus RL. RS plus RF plus RL. So this will give us Im square by 2 into RS plus RF plus RL. So this is the AC power input. So the rectifier efficiency is defined this way. The rectifier efficiency is defined as the DC power output divided by the actual power input to the half wave rectifier. So that is the value of the rectifier efficiency. So rectifier efficiency we call it as eta. So that is equal to PDC divided by PAC. So what is PDC? 4 Im square by pi into RL divided by Im square by 2 into RS plus RF plus RL. Now the diode forward resistance and the transformer's secondary winding resistance are negligible compared to the load resistance. So neglecting the values of RS and RF, we get this as 4 Im square by pi into RL divided by Im square by 2 into RL. So this will give us the value as 8 by pi square. So this will give us the value as 81.8. So the rectifier efficiency for full wave rectifier is 81.21%. And what is the corresponding value for half wave rectifier? For half wave rectifier, the corresponding value is eta value for half wave rectifier is 14.6%. So you can say that the efficiency is almost double. The efficiency is double in case of full wave rectifier compared to its value in half wave rectifier. It is more efficient. Why it is more efficient full wave rectifier? Because the power is present both for positive half cycle and the negative half cycle. In half wave rectifier, only power or only the output is available for only half of the cycle. So one half of the input is wasted in the case of half wave rectifier. So naturally, the rectifier efficiency is double for full wave rectifier. It is 81.2%, and for half wave rectifier it is 40.6%. Next is the ripple factor. So what is the ripple factor? Ripple factor indicates what is the amount of fluctuations in the output. See, ideally we require a DC output, so without any fluctuations or without any variations. So the output, it is not ideal, it is not pure DC for half wave rectifier. There are some amount of slight variations. So the output is not pure DC. So because output contains some amount of pulsating components. So ideally the output should be output variations should be zero. So that means we expect an output like this. We get some fluctuations like this. So ripple factor indicates how smooth is the output. It is a metric for the performance of the rectifier. And the rectifier, it is calculated this way. The ripple factor is calculated IAC divided by IDC. That is the definition of the ripple factor. So what is IAC? IAC is equal to IRMS square minus IDC square. So divided by IDC. So this is how the ripple factor is calculated. And what is, we can say this is equal to IRMS square by IDC square minus 1. So what is IRMS square? You know, it is IM by root 2 whole square. And what is IDC? It is 2IM by pi. 2IM by pi minus 1. So this is equal to IM square by 2 into pi square divided by 4 IM square minus 1. So this will give us the value pi square divided by 8 minus 1. So this is the ripple factor for full wave rectifier. What is pi? Pi is 3.142. So you multiply, you square it, so we get approximately 9. So 9 by 8, so this is equal to approximately 9 by 8 minus 1. So what is 9 by 8? Okay, so we get approximately 0.14. So the ripple factor, and we have to take the square. We have to take the square root of it. So the ripple factor we get much better than the half wave rectifier. So here it is pi square by 8. We get, once we take the square root of it, we get the ripple factor as 0.48. So the ripple factor indicates that the ripple contents the output are 48% the DC component, which is much less than that for the half wave rectifier. Now let us summarize what we have discussed. So the main disadvantages of half wave rectifier are it is a simple circuit and it is a low cost and it is very cheap. The disadvantages are, we have discussed and we have seen also now, that the transformer utilization factor is less with a low output voltage, and also it causes the DC saturation of the transformer. The power output and the rectification efficiency are also quite low, and the ripple factor is very high. That means the output is not smooth. So to overcome this, we go for the half wave rectifier, which essentially contains two diodes D1 and D2 and the load resistance. And the transformer is little complicated here. In the case of full wave rectifier, it is a center tapped transformer. And the operation of the circuit, when the input is positive, so here there is a positive cycle and here there is a positive cycle. D1 is forward biased, so it is replaced with a closed switch and the current passes through the diode in this direction. And during the negative half cycle, D1 is reverse biased and D2 is forward biased, and the direction of current is in this way. So in both positive and negative half cycles, the current through the load resistance is in the same direction. So we get output for both positive and negative half cycles, and this is the output. So this is the output for the positive half cycle and this output for the negative half cycle. So we have calculated the DC current, and how we have calculated 1 by pi into 0 to pi and IL d omega t. So 1 by pi into 0 to pi into Im sin omega t d omega t. So that gives us the value as 2 Im by pi. And what is the corresponding value for half wave rectifier? It is Im by pi. So it is double for the full wave rectifier. The average DC voltage is, we apply the Ohm's law and IDC multiplied by the RL. So that is equal to 2 Im by pi into RL. And the corresponding value for the half wave rectifier is Im by pi multiplied by RL. So this is for half wave rectifier. And the EDC value in terms of voltage, maximum amplitude of input voltage, it is written like this: 2 ESM into RL divided by pi into RF plus RS plus RL. This is a diode forward resistance. Okay, so that is equal to 2 sum by pi into 1 plus RF plus RS plus RL. So when the load resistance is more than the forward resistance and the transformer secondary coil resistance, we simply write EDC as 2 sum by pi. And RMS value of the load current is 1 by pi into 0 to pi into IL square d omega t. So IRMS is equal to 1 by pi into 0 to pi Im sin omega t whole square into d omega t. So IRMS is equal to Im by root 2. Im by root 2. And correspondingly, the voltage, RMS value of voltage is IRMS multiplied by the RL. So that is equal to Im by root 2 into RL. Okay. And the DC power output, we multiply the output voltage with the output current. So the output value of the DC voltage with output value of the DC current. So that is equal to IDC square RL, and PDC is equal to IDC square multiplied by RL. IDC we have calculated as 2Im by pi. So 2Im by pi whole square into RL. So PDC is equal to 4Im square into RL by pi squares. So this is the DC power output. And the AC power input, it is, we take into account the transformer secondary coil resistance, which is RS plus RF plus RL. So IRMS square, when it is multiplied with RF plus RS plus RL, it gives us the value of AC power input. Okay, and the rectifier efficiency eta is equal to PDC by PAC. So that gets simplified into 8 by pi square, which is 81.2%. Whereas for half wave rectifier, we have seen that it is 40.6%. This is for half wave rectifier. The ripple factor. The ripple factor, it indicates how smooth is the output. So ideally, there should not be any variations in the output. The output should be a perfect DC, but in reality, we don't get a perfect DC. We don't get output like this. We get a small amount of fluctuations like this. So the ripple factor, it indicates how smooth is the output voltage. So the ripple factor we have calculated as 0.48 for the full wave rectifier, which is much less compared with the half wave rectifier. This you can understand because in half wave rectifier, for the second half of the input wave, the output is 0. Whereas in full wave rectifier, we get output both for positive cycle and negative cycle. So we get a better output with less ripple for the full wave rectifier. The peak inverse voltage, this is a very important parameter. The peak inverse voltage parameter, it indicates what is the maximum voltage the diode experiences during the operation of the circuit. So that is the peak inverse voltage. So you see here, when this D1 is forward, this is the D1, when D1 is forward biased and D2 is reverse biased during the positive half cycle, you know, this it is like this and it is like this. So in this case, the diode is reverse biased. So what is the maximum voltage you get? Here you get minus Vm, and here you get plus Vm. So the peak inverse voltage is 2 ESM for full wave rectifier. And what is the corresponding value for half wave rectifier? It is ESM. This is the only disadvantage of full wave rectifier. You have to choose the diodes with maximum value of operating voltage. So the diode should withstand more voltage in the case of full wave rectifier, because the diode gets peak values from both ends. Here they get minus Vm and here plus Vm. So it gets 2 Vm. So the peak inverse voltage of the diode is 2 ESM. So you have to choose the diodes with maximum ratings. Otherwise, what happens? If we choose the diodes with less value of ratings, the diodes are likely to get damaged during the operation of the circuit. So, in summary, the advantages of full wave rectifier are the efficiency is higher and there is a large DC power output. The ripple factor is less. So, these are all the advantages of full wave rectifier. Advantages are the efficiency is higher, the DC power output is high, and the ripple factor also is less. What are the corresponding comparisons? The average value of DC current. I'll just summarize here. This is full wave rectifier and this is half wave rectifier. So if you see the average DC current, so IDC value, it is 2 Im by pi, whereas it is Im by pi. And what is the load current, DC value of load current here? The DC value of load current is 2 ESM by pi for full wave rectifier, whereas here it is ESM by pi. Okay. And what is IRMS value? IRMS is Im by root 2 here, whereas here it is Im by 2. What is the RMS value of voltage? So ERMS for full wave rectifier is ESM by root 2, whereas here it is ESM by 2. Okay. And what is the rectifier efficiency? The rectifier efficiency here it is 80.1%, 81.2%, whereas here it is 40.6%. Okay. The ripple factor here it is for full wave rectifier it is very less. So these are all the various advantages of the full wave rectifier. What are the disadvantages of full wave rectifier? You require, just now we have discussed that the PIV, which is nothing but the peak inverse voltage rating of the diode is higher. So higher PIV diodes are larger in size and they are costly. And the cost of center tap transformer also is high. For a half wave rectifier, you can use normal transformer, whereas for full wave rectifier, we have to use the center tap transformer, so the cost is high. So these are all the disadvantages of the full wave rectifier. So with this, I conclude today's session on the full wave rectifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.